Chapter 3, Section 4 talks about linear programming. Linear programming just allows you to maximize or minimize real-world objects. And before we do the whole real-world application, we need to get used to the process of graphing these things and seeing what our options are. So in the first couple of exercises, they're going to give you inequalities. You graph them all on the same coordinate plane, and then we'll talk about some other keywords like objective functions and things like that. So taking a look, I'm going to try to color code these, might make it a little bit easier. I'll do this first inequality in red. It is not in a graphable state because at this point it's not y by itself. So I'm going to take a second and do that first. In order to get y by itself, I'm going to start by subtracting 4x from both sides. I'm left with 5y is less than or equal to negative 4x plus 35. And dividing everything by 5 gives me y is less than or equal to negative 4/5 x plus 7. And before I keep going, I'm going to graph that. That's a line that starts at positive 7, goes down 4, and over 5. It's a solid line, although you'll find that almost all of these are. Now, the shading for this would be below. So I'm going to start shading, and then I'll erase as necessary as we keep adding these keep adding these constraints in. So below this red line happens to be all of this. Even below the first quadrant, really, that's part of it as well. All right, next line I'll do in blue. 5y plus x is greater than or equal to 20. I'm going to start by subtracting x from both sides. I get 5y is greater than or equal to negative x plus 20. And dividing by 5 gives me y is greater than or equal to a negative 1/5 x plus 4. That is a line that starts at positive 4, goes down 1 over 5. Also solid, again, your constraints usually are. And we're shading those things that are above the blue line. So what I had shaded before, I'm just going to start taking things away. I can no longer be below the blue line because it's greater than that. So I'm going to take away any shading that's below the blue line. It's not included anymore. Now, I'm not sure if you picked up on it or not, but I'm using the word constraint for these inequalities because that's what they're called. We'll go over vocabulary a little bit as well. There are two constraints that are very often included with linear programming, and the first is y is greater than or equal to 0. So y is greater than or equal to 0. Color, we can do that one. Y is greater than or equal to 0 is a line that's horizontal, and it lies right on the x-axis. This is often part of your constraints because they keep all of the values in the first quadrant. And then the other constraint that we have is x is greater than or equal to 0 is also just a straight line that's not diagonal, but that one happens to be the y-axis. Again, keeping all of your values in the first quadrant. So what you do next is you pick the ordered pairs of the corners of the shaded area. So if you look at the shaded area, it forms a triangle. This is a vertex, that's what those are called. Here's a vertex, and there's a vertex. Those three ordered pairs, I'll start at the bottom left. That ordered pair is 0, 4. The one above it is 0, 7. And the one on the right is 5, 3. You take each of those ordered pairs and you plug them into the equation that starts with p equals. So I'm going to put all my x values in and all my y values in. When I put in a 0 for x and a 4 in for y, I get p equals 8. When I put in a 0 for x and a 7 for y, I get p equals 14. And when I put in a 5 for x and a 3 for y, I get p equals 46. Now, each question will tell you whether they're looking for the maximum number or the minimum. This one does not, so I'm actually just going to assume it's maximum. So my final answer is 5, 3 max at p equals 46. And I know this doesn't really make much of a difference to you right now, but that's how you do linear programming. You graph all of these linear inequalities on the same xy axis, and then you determine where the area is that they overlap. You pull the vertices and you see what your P equation value is for each vertex. Now I'm going to give some vocabulary to these things. We talked about how to do it. Let's talk about what they're called. In linear programming, the inequalities you're given originally are called constraints. In this problem, it's all of those. Those are my constraints. Constraints are restrictions or rules that are put in the real world problem. You'll see those a little later on. They're things like you don't have more than 100 hours to work, or you only have 15 cups of flour to make the recipe, or you only have sweatshirts or 20 sweatshirts you can silk screen. So you'll notice the constraints are restrictions or rules that are put on real world objects. Now, those are called constraints. When you graph your constraints and you shade everything, you end up with a shaded area. In this case, it's yellow. I highlighted it yellow. That is called the feasible region. The feasible region contains all of the ordered pairs that satisfy all of the constraints. When you find out where that feasible region's boundaries are, you get what are called vertices. In this case, we had 3 of them. Vertices help determine what your maximum or minimum objects are because they're the boundaries of your feasible region. You take those vertices and you plug them into the objective function. You'll notice the objective function is usually P equals because it stands for profit. In these situations, we're usually trying to maximize our profit. So again, you graph all of your constraints to find a feasible region. You pick out the vertices, plug them into your objective function to find out where you can maximize your profit. All right, new problem. Again, I will try to color code. Makes things a little bit easier for you. I'll do this top one in red. If I subtract x from both sides, I get y is greater than or equal to negative x plus 2. So that's a line that starts at positive 2, goes down 1 over 1. It's really tiny, very close to the origin. At this point, I'm shading above the red line. So technically speaking, and I'm going to erase this in a second, that's all of this. All of that is still part of my feasible region, so I'm not going to shade it until I narrow it down a little bit. The next inequality I'm going to look at is x is greater than or equal to y. I actually don't like that it's written like that. I'm going to switch it, make it y is less than or equal to x. That's a line that starts at the origin and has a slope of 1. Get that blue line up there. Now we're only talking about values that are smaller than the blue. So bigger than the red and smaller than the blue at this point is all of this. Bigger than the red and smaller than the blue. I'll leave that yellow highlight there and we'll take off what we need to. The next constraint that I see, I haven't used green yet, x is less than or equal to 4. X is less than or equal to 4. If you have just an x, that's a vertical line, and we want it to be less than that line, so I don't want to include anything on this side. And get rid of all of this shading on the right. Those values are not less than 4. So now my feasible region's getting much smaller. And the last constraint that I have, y is greater than or equal to 0. Remember we talked about this in the last problem, is actually the x-axis. So that's what's going to cut off all of this leftover feasible region underneath the x-axis. Very often that's not part of it. So you'll notice my feasible region has a little bit of a different shape this time, not a shape we're used to. So I'm going to kind of put circles where my vertices are. Anywhere that the lines meet is a vertex. I'm going to start my ordered pairs. The first one I see is 1, 1. Then moving in a clockwise fashion, I have 4, 4. And then down on the x-axis, 4, 0. and then over 2, 0. So I need to put each of these vertices in the objective function one at a time and see what value we get. Often in our heads, we think that the largest ordered pair will maximize, and that's not necessarily the case. All right, putting a 1 in for x and a 1 in for y gives me 4. Putting a 4 in for x and a 4 in for y gives me 16. Putting a 4 in for x and a 0 in for y gives me 4. And putting a 2 in for x and a 0 in for y gives me 2. So I'm maxing out at 4, 4, where p equals 16. This is linear programming. Pause the video to do the U-try. You'll notice this feasible region had several constraints that went up and down. I do want to point out the compound constraint that was there. 1 is less than or equal to x is less than or equal to 3. Remember, that was a sandwich, both vertical lines, and you shade in between. So the whole reason we've been doing this linear programming is so that we can apply it to real world problems, often in the business department, where you have profits and restraints and things like that on your business. So the first word problem that we're going to do, I will tell you that these are really overwhelming, and I understand that, so I tend to follow the same steps. So first thing we're going to do is read through it. Your school band is selling calendars as a fundraiser. Wall calendars cost $48 per case of 24. You sell them at $9 per calendar. Pocket calendars cost $30 per case of 40. You sell them at $3 per calendar. If the band can buy no more than 1,000 total calendars and spend no more than $1,200, how can you maximize your profit if you sell every calendar? What is the maximum profit? So, first thing I would do is define your variables. Decide whether you want one thing to be x or one thing to be y. In this case, it honestly doesn't matter, so I'm just going to do them in order. I'm going to let x equal my wall calendars, which means y equals pocket calendars. Now I'm going to record all of the info. Wall calendars. They cost $48 per case of 24. So I need to talk about cost for each of them. If it's $48 for 24 of them, then they're $2 each. You're dividing. Always take however much your bill is divided by however many you are. I can sell them at $9. So they cost $2. I sell them at $9. Let's take a second and consider that. How much do you make on each calendar? If each of them costs $2, but you sell at $9, you profit $7 each. Subtract. Your profit is how much you sell minus how much they cost. All right, pocket calendars. Pocket calendars cost $30 per case of 40. So again, if you divide, do 30 divided by 40, you get 0.75. So they cost, I'll do $0.75 each, that's 75 cents. And they tell me I can sell them for $3. Sell them for $3 each. So my profit, I can not write it this way, hold on. My profit, if I subtract, is $2.25. Remember, your objective function, which is called P, is profit. So we're going to save those values for profit. Okay, the first thing I noticed, and we're going to start making our constraints now. We've recorded all the information, let's make some constraints. I know that I can buy no more than 1,000 total calendars. So think about that. That means that wall calendars, X, and pocket calendars, Y, has to be less than or equal to 1,000. It says sell no more than 1,000. That's my first constraint. It also said I can spend no more than $1,200. So this is how much I'm spending. This is their cost, how much they cost. Okay, so each of the wall calendars cost 2, and each of the pocket costs 75 cents. I can spend no more than, so less than or equal to $1,200. All right, and the last question is kind of important, but we tend to forget it. What additional constraints must be satisfied because the problem involves real objects? That's always going to be x is greater than or equal to 0 and y is greater than or equal to 0 because you can't have a negative amount of calendars. So I'm going to pause the video for 1 second and move my constraints to the next page. Okay, so we have to develop our objective function. Sometimes they'll give you the objective function, here they do not. And remember, we're talking about profit. So how much profit will the band make on wall calendars? And we already discussed it on this slide. Wall calendars were $7 profit and pockets were $2.25. Sorry, I got interrupted. Kind of lost where I was. I'm hoping here's where I was. The profit that the band makes on wall calendars is $7 each. So I'm actually going to write 7x. Because remember the word each implies multiplication. And the profit that they'll make on pocket calendars was $2.25 each. So if we wanted to talk about an overall objective function, we would take 7x plus 2.25y. That would give me the total profit I made on pocket and wall calendars. So moving all of this information over to the other side, I had already added my constraints. I'm going to take a second, get my objective function up there as well. All of your stuff is on one side. All right, we're going to graph these first. This top one up here, if I solve that for y, I get y is less than or equal to negative x plus 1,000. Oh my goodness. At this point, these numbers are huge. So I'm going to play a trick. I'm going to play a trick and say, instead of going by ones, because my graph only goes up to 10, I'm going to say that all scales by 100. Okay, so if I wanted to go to 1,000, I have to go all the way up to 10. And then because all scales go by the same, including the x-axis, my slope of down 1 over 1 is easy. I can just count it off like a normal slope, down 1 over 1. Take a second, get that line up there. And that first objective function keeps me below the red line, so less than or equal to. For the second objective function, I'll do that one in green. I get y is less than or equal negative 8/3 x plus 1,600. All right, now this one's crazy because I really should start at 16, and that's not on my graph. So imagine as if I started at 16. If I want to go down 8 from 16, I'm at 8. Then I can go over 3. That's my first point, and then down 8 again and over 3 will get my second point that I can graph. That's crazy, so let me say it again. That 1,600 y-intercept is really up at 16, but I don't have a 16 on my graph. So instead, I pretend I start at 16. Going down 8 would put me at 8, and then I went over 3. So that's my second constraint graphed. And this one, because of my inequalities, I'm going to be below the green. So I'm below the red, below the green. And then, of course, my last two, I'm actually going to put them both in under the same color. So I used red. I'll use blue this time. Is just my x and y axis. Keeps me in the first quadrant. So my feasible region here is below everything. It ends up being all of this. It's feasible region. Now, here's one of the trickiest parts when you change your scale. When you pull out the vertices, your scale has changed. Keep that in mind. So I've got 4 vertices. One of them is below my recording box. It's the origin, so I can't write that down, or I can't show you, but it is 0, 0. Every one of those vertices has 100 in it. So even though my first ordered pair looks like 0, 10, it's actually 0, 1,000. Okay, and that one in the middle that's kind of really in the middle, I'm going to call that 350 and 650. Remember, I'm by hundreds. And then the last one on the x-axis would be 600 and 0. So we're going to take a second and find our profit for each of these. Go ahead and do that in your calculator. Pause the video, do that in your calculator, and come back. So I'm really hoping as you did the objective functions, you discovered something crazy. You should, oh, I think I made a mistake here. Anyway, you still discovered the same thing, sorry. you should discover that your maximum profit actually doesn't occur at 350, 650, which is probably what you expected to happen. Your maximum occurs at 600, 0. That means that we should be selling 600 wall calendars and 0 pocket calendars. We should not be selling pocket calendars because we would lose money. And our maximum profit would be $4,200. Oh my gosh. So linear programming is really important because in a situation like this, you expect to be able to say that you would just sell as much as you can. But given the restraints of 1,000 calendars and $1,200, you don't even want to sell or pocket calendars. They wouldn't give you the profit that you needed. So linear programming has its uses, that's for sure. All right, a lunch stand makes 75 cents profit